All right. So welcome back. Let's get started with the next session. Yeah, our next session is a very special one where we have talks by researchers from our industrial partners. A few words about our industrial partnership program. This actually provides an invaluable forum for us to engage with researchers in industry in a close manner. And it also, very crucially for us, provides valuable support which we use towards our program and research visitors. We have many returning industrial partners today, Apple, Google, Jane Street, Oski Technology, NVIDIA, and ADIA Lab, as well as we welcome two new partners, Bridgewater Associates and Stellar Foundation. So some partners, in addition to the general support, also provide additional targeted support, such as, for example, the recent AI for Math initiative, which is generously supported by Google, and Jane Street, where we have a new initiative called Circles or Small Group Collaborations, and they also support some of daily teas and a mega reunion of all recent machine learning programs that is in planning for next year. And Bridgewater has also provided us additional funding for our postdoctoral researchers in machine learning for the next couple of years. And as the Institute's new director, is actually one of my top priorities to amplify our industrial connections and partnerships. Our partnerships really provide a custom set of benefits that are aligned with the needs and interests of the partner. And we really welcome your ideas and suggestions in this regard. And if you scan the QR code on the pamphlet outside, you will actually get a booklet which describes the activities of today and also has some information on our industrial partnership program. But as I said, it's always customizable to what makes most sense for each company. So with that, we're ready for the next session. Just two quick reminders. One is, please, I don't see anyone with coffee or anything. That's great. So Amy was effective. But yeah, please no food or drinks in the auditorium other than water. And Amy here is our timekeeper. So please adhere to time. So we have 6 talks in this session, I believe. And the first one is by Hilal from Apple on bridging central and local DP.
Great, thanks for the intro. Can you guys hear me? Yeah. Okay, hopefully it works. Okay, so I'm going to talk about private aggregation in the federated setting. And so the background here, the black background is not super clear. So if something is not obvious, you can always look at the monitors there. They look a little bit brighter with black. So And I'm going to briefly talk about 2 joint works with some great collaborators, 2 of which are here, Kunal and Vitaly. Okay, so the motivation is the federated learning setting, which Nati gave a great intro on in the early session, where basically we have devices and that have sensitive user data. Think about like emojis, text, and so on. And the goal is to use this user data to learn something useful that is going to improve the user experience. Think about like trying to predict the next word or which emojis the users are going to use and so on. Unfortunately, this data is very sensitive. And so it has to stay on device. And so the goal is going to be to try to do this learning process in a distributed fashion. More generally, we might want to do training machine learning model in this way, in this distributed fashion. So here, usually the server will send the model to the devices that are going to download the model, calculate some sort of gradients based on their data, and then send their updates to the server that's going to update the model and keep doing this iteratively. So this is the main topic that I'm going to discuss in this work, and I'm going to try to zoom in on one round of this iterative protocol, where each round we have users that have vectors, high-dimensional vectors. You can think about these vectors as being the gradients of each user. Think for simplicity, each vector being unit norm, and our goal is to estimate the mean or the summation of these vectors. We measure there using the L2 error. So as most of you already know, this federated learning is usually not private. So you can actually reconstruct some images or text and so on from the gradients that the user sends. And therefore, usually you need some extra work in order to guarantee that these protocols or federated algorithms are private. And so this is what we try to do in this talk. And we do this using differential privacy. I'm not sure if everyone here is familiar with DP, so I'm going to give like a quick definition or like intro to DP. Okay, so the way DP works is basically says, assume you have two data sets, and where only one user is changed. So like you just change the last user in the second data set, and you apply an algorithm on these two data sets. So DP basically says that the output of the algorithm, the way the algorithm behaves, is going to be very similar on these two data sets. So in some sense, each user cannot really affect the performance or the behavior of the algorithm too much. So mathematically, it basically says that the output distribution of A of x is very similar to A of x prime up to this like factors of like additive term of delta and the e to the epsilon in there. So think about epsilon being like 1 or 0.1 and delta being negligible. This is very like strong notion of privacy. It prevents memorization, membership inference attacks, and so on. So this is very powerful both in theory and in practice. In the context of the federated setting, there are different ways to try to apply differential privacy. One is the central model of privacy, which is like perhaps the more well-known model, which basically says that we assume that the server is actually trusted, so the users trust the server, and the server has direct access to the data of the users. And what the server releases is actually a differentially private version of the output. So basically, the output of the server is private, but the users trust the server with their data. Usually, this results in very good utility because the server has direct access to the data. Unfortunately, this is usually a little bit too strong in practice because the users may not trust the server. And so that's why there is the local model of privacy. This is also an old model of privacy, where the devices do not trust the server. So here, no one trusts the server. So basically what the devices will do, they will apply a differential private protocol before sending their data to the server. So in some sense, think about like the users as adding noise to their gradients before sending them to the server. So this is great from the privacy perspective. However, this is not good in terms of utility. Because the server does not directly see the data of the users, it usually ends up being a little bit worse in terms of utility. So what we try to do in this line of work is basically, can we come up with intermediate models of trust where basically we have, or we require less trust from the users, so the users don't have to trust this like central model, but at the same time try to come up with like better protocols and better performance accuracy. Because as I said, the local model is usually a little bit too weak. It doesn't really give good performance in practice. So the way it has been happening in the privacy literature is basically that people come up with like primitives that are usually easy to implement in a secure way. Think about crypto techniques that allow, like for example, to implement aggregation using multi-party computation, for example. So these are primitives that are easy to implement in an efficient way using crypto techniques, but at the same time, they allow us to do a lot of tasks in the federated setting more efficiently than in the local model. So for example, one such primitive is basically a shuffler, which basically says that before sending the messages to the server, I'm going to have like an intermediate shuffler that takes all of these messages and shuffles them. So the server doesn't really know which user sends which messages. It turns out this is actually extremely useful for many applications, and it allows to achieve, for many applications, the same guarantees as the central model, with, again, much less trust needed from the users. So here in this talk, we focus on the vector aggregation. Again, we have gradients. We will try to aggregate them. And the question is, does the shuffle model, like, where does it come in terms of utility? Like, does it achieve the central DP guarantees or not?
Question?
Yeah.
Kind of two integers, the length of each individual vector and the number of individual vectors. How do those two numbers compare in general usually?
Wait, so there's the dimension of the vector, and what else you say?
The number of...
the number of users.
Yeah.
Exactly. Both of these are important. So you see, in the central DP model, the error does not depend on n. So this is the error, I mean, for summation, not for mean. So for summation, your error is like square root d over epsilon. Unfortunately, in the local DP, the error also depends on n. N is the number of users, and d is the dimension. So this is extremely larger than that, and usually this becomes not practical.
No,
but I'm not sure if
I'm a practical question, like how relative number of users versus length.
Oh, I see. So it depends on the setting. Usually, like If you think about like training large models, then D will be large, like let's say like hundreds of thousands or millions and so on. But N like will be like the number of users in each batch. Think about like thousands or tens of thousands. So N is usually smaller than D. Okay, so again, this is the question, like what happens in the shuffle model. People have cited this question in the one-dimensional case, and they showed that in one dimension, if each user sends like a single message, then you cannot achieve the central DP guarantees. But the good news here is that if you send 1 plus little of 1 messages in expectation per user, which is like pretty good, then you get the same guarantees as central model, which is very good. Unfortunately, the situation is a bit more complicated in the D-dimensional setting, and it turns out that you cannot extend this easily to the D-dimensional setting. The same protocol will usually result in exponential in the number of messages, which is too expensive. So the main question in this work is, are constant number of messages sufficient to get the same guarantees as the central model? And if not, how many messages do we need in order to get the same guarantees? So what we show in this work is that there is a protocol in the shuffle model that takes order of the messages per user and gives you the same guarantees as the central model. So this is significantly larger than constant number of messages. And we also show that actually this is also sufficient. Like you can actually get away with smaller number of messages. Like you have to really send D messages per user in order to somewhat hide the users among the set of different messages. I'm going to briefly talk about the technique. So for the upper bound, the technique is basically using Gaussian representation to somehow distribute the signal across all of the coordinates, and then we apply the one-dimensional protocol for each coordinate. I don't want to dig too much into this. I want to talk a little bit about the lower bound. The lower bound is basically based on the idea that if each user sends a small number of messages, then we can provide a reconstruction attack that returns a small set that basically reconstructs the input. So how is this going to work? Assume you give me like the set of shuffled messages. Each user sends k messages, so I have like a set of nk messages. I'm going to do a simulation of the protocol, which basically construct the data of the first user. So I'm going to pick k messages out of these messages. I'm going to assume that these k messages were sent by the first user. And I'm going to simulate the other users to have 0 input. So I'm going to basically simulate the protocol of them having 0 input and see what messages they send with this input. And then I'm going to run this protocol. And so the claim here is that if I were to pick these messages here correctly, like the messages that belong to the first user, then what this protocol is doing, it's basically summing the inputs of all of the devices, and therefore it will basically approximate V1. So what this basically says that if you go over all the set of messages of size k, this will basically reconstruct the first input or all the inputs, and this will give you a set of size n to the k. Now the question is like, why is this good? This is good because this will usually violate privacy if k is too small. Because what privacy says is that any reconstruction of the input basically must be extremely large. Basically, the algorithm does not really learn anything about the input, which means that if you think about the d-dimensional space and do some sort of discretizations, this means that the size of the reconstructed set has to be 2 to the d if you are private. You do not really learn anything about the input. And so this will basically imply that k is larger than the overlog n. So basically what we showed here is that shuffle DP will get the same guarantees as central DP. But the unfortunate news is that you really need to send D messages per user. And this D messages really is a lot of overhead in practice because each message has its own overhead in terms of communication and efficiency. And so like this is way too expensive to do in practice. So the next question is like, are there other models that are better in terms of like secure aggregation, in terms of like private aggregation? And the next model is basically secure aggregation, which has become more popular recently, which basically says that the users are going to send their data to some intermediate, or like there is like a primitive which is basically provides like some secure aggregation of the inputs of the users. And this is usually easy to implement using crypto techniques. So using this, it's very easy to get the same guarantees as the central model because each user can basically add some small Gaussian noise to their data, and then after summation, all of this Gaussian noise will be added. So this is pretty straightforward. And this is also usually easy to implement using crypto techniques in the 2-server model where the servers are not colluding. by basically sharing 2 secret shares with each of the servers. So basically, if your input is V1, you're going to share some random noise R1 with the first server and V1 minus R1 with the other server. So each server doesn't really learn anything about the inputs, but the outputs of these 2 servers, when they sum them, you can basically reconstruct the original sum. The problem here is that there is, again, also overhead in communication in the sense that each user has to send now order of the bits. So the number of messages is good, but still you have to send a lot of bits. So how can we overcome this? We come up with a new primitive which we call preamble, which basically allows us to exactly solve this problem and get the same utility as central DP, at the same time also get much better communication, order of n epsilon squared. Again, to your question, so this is, because n is much more than d, this turns out to be very useful in our kind of settings. I have 1 minute, so I'm going to briefly talk about what kind of techniques we use for this primitive. The first one is basically what have been used a lot recently in the federated setting, which is basically using random projections to try to reduce dimension. So we're going to use a random projection to reduce to m dimensions. And the crucial idea here is that we're going to use the number of dimensions m so that the projection error is less than the dp noise. So remember that we have privacy here. So privacy means that we have to add noise. So we can pick m so that the projection error is smaller than dp noise, and therefore we don't pay at all for projecting the inputs. The second idea, which is actually, it's a very nice line of work from the crypto community on this. It's called distributed point functions. It allows to securely aggregate 1 sparse vectors. So if you give me like 1 sparse vectors, then I can securely aggregate them using polylog communication. So this is very useful. It turns out that this becomes too expensive for k-sparse vectors. And one key idea we use here for like trying to extend this to the k-sparse setting is basically trying to block the vectors into blocks and sending k-sparse blocks instead. So we have some correlation in terms of like which coordinates we send. We show that this correlation is still fine in terms of utility, but having this correlation allows us to become practical. And finally, we have we do need some privacy amplification by sampling. And the reason is because of this random projection, usually you will rescale the inputs or the noise by the d over m factor, because you're subsampling, so you have to rescale to make things unbiased. And so this rescaling will actually increase the noise by significant factors. It turns out that we can use amplification by sampling results to show that the same noise as central DP is actually sufficient in this case. And the idea here is, again, the crucial property of these DPFs is that the anonymity of the blocks. So the blocks that each user sends are basically anonymized by the secure aggregation protocol. OK, I think I'm out of time, but I just want to briefly give like 2 experiments that we did. One is like basically trying to plot the error as a function of communication cost. And here you can see that the preamble basically gives almost the same performance as the Gaussian mechanism at like almost 100 improvement in terms of communication. We also have some simple experiments for CFAR showing that, again, DPSGD with preamble also gives you similar performance to the Gaussian mechanism with much smaller communication. To conclude, I think it's important to study intermediate models between central and local DP. I think there's room for like new primitives, simpler primitives, and also exploring new tasks like beyond aggregation, like selection, and so on. Yeah, thanks everyone, and happy to take any questions if there is time.
Maybe we'll take one question and the next speaker sets up.
I'm not an expert on DP, but when I look at it from the mathematics standpoint, what I understand is that you're modulating some signal as a way to hide the real information, right? To then reveal some information about that endpoint. And you have this shuffling algorithm in the middle that you presented, where it added each line of messages, right, as a summation. As an engineer, when I look at something like that, I think of fast Fourier transform. Things like you have multiple lines of signals that can be summed up and represented, and if I can modulate one of them, I can have my own build a differential privacy algorithm of some kind. Is that a reasonable thing to assume, or is there some difference that you're doing in terms of signal manipulation beyond that?
So I guess
Maybe it's too complicated, but whatever you want to take.
yeah, I guess we can take this offline because I'm not sure I completely understood the question. But I think the thing is that the idea is to try to come up with simple primitives that you can do in a distributed fashion that are general enough to allow to do a lot of different algorithms. So like summation and shuffling are very simple primitives to implement, and they allow us to do a lot of different tasks just from these two primitives. But we can talk offline.
Thank you. Thanks again for the talk. Yeah. So next we have Rohan Alur from Bridgewater telling us about judgmental forecasting with LLMs.
All right. Hi, everyone. Thank you for having me. I'm here to give the obligatory talk on LLMs. And so this is based on some joint work with my colleagues at Bridgewater, and in particular as part of our IA Labs research group. Okay, so I promise I am going to get to LLMs, but I want to motivate this work with the following puzzle, which is that we've known for a long time that algorithmic predictions, even predictions that are produced by very simple algorithms, will usually outperform human forecasters. And when I say a long time, I don't just mean, since AlexNet or ChatGPT or something like that. You can find social scientists making this claim as early as the 1950s, where people would find that even very simple linear models or contingency tables will outperform human experts in things like clinical diagnosis. But of course, now almost 70 years later, we know that human discretion is still involved in virtually any high-stakes prediction task that you can think of. So we're going to ask why. And so to understand this, I want to just consider the following thought experiment, which is how you would forecast the sale price for a house in Berkeley. You know it's going to be a large number. You just don't know exactly how large. So I think one reasonable approach to start with is you would say, I'm going to find similar homes and take the average of their historical sale prices. You might say, well, OK, I don't know how to define the right similarity function. But that's fine. This is the kind of thing that modern statistical learning algorithms are very good at. Right? So for example, Zillow has an algorithm for this. They claim it has a median absolute error of less than 2%. And that seems sufficient for most purposes. But of course, what if this is a house that you really care about in particular? It's your house, and you want to know the sale price. And you bump into your neighbor, and they tell you, the foundation of my house is shifting. You should probably get the foundation for your house checked out as well. And so this is probably bad news for the sale price, but it's going to be hard to quantify, right? Like historical precedents are going to be hard to find. And I think even more importantly, maybe if that data exists in principle, it's going to be difficult to coerce into a format that's amenable to any kind of statistical analysis, right? I think this is sort of a more general theme. You might hear this called the broken leg problem in some of the social science literature for reasons that are a little contrived, so I won't get into it. But really it's making this observation, right, that machines excel at inductive reasoning or extrapolating from low-level patterns, but at least historically they really struggle with deductive reasoning, so symbolic reasoning, understanding things like abstraction and causality. And this will often motivate the use of humans to oversee algorithms, right, because even if these algorithms are correct on average, they're going to struggle with special cases. And I think you can see this tension, in the history of AI research. Very early inductive methods like, the perceptron, for example, then got replaced at some point with expert systems, symbolic reasoning engines in the 70s and 80s, as people were trying to design, for example, systems to play chess that need to handle board configurations that they've never seen before. Okay, but I promised I would get to LLMs, and I think if you're a believer in the bitter lesson, you might say this is actually there's no tension here at all. Right, that LLMs are trained inductively, on this next token prediction task. But if you do this with enough data and enough compute, in particular with enough heterogeneous data, you get something that starts to look like deductive reasoning abilities. Right, so you get these, I think, very cool but also kind of unnerving charts that show that LLMs can now perform tasks that take a human programmer something like 2 hours. And so I want to convince you that this judgmental forecasting problem is an interesting way of measuring AI progress, right? So the goal is going to be to forecast the outcome of a future event, so something like a home sale price. But unlike in your typical Kaggle setup, you're not given any training data. So the model, like a human, can draw on its past experience, and it can proactively gather information. but it's not going to be provided with any training data. And so we're going to ask, can LLMs do this? Hopefully you're convinced that this would be, very interesting in its own right. But it's also, I think, a very natural benchmark for more general capabilities, right? So this problem stresses these abstract reasoning abilities for these models, and you also have verifiable rewards, right? So very much in keeping with, the history of using chess and then Go and then poker and more recently math and programming as benchmarks where you can compute a verifiable reward signal and use that to bootstrap improvements. So we built a system that does this. So you can put in, a question like, will the US government allow China to import Blackwell chips by the end of next year? And it'll spit out a probability. And it will also give you a long report. So I'm just excerpting part of it here, but it gives you a few pages to sort of support this probability. And it has many problems, but we think it's pretty good. So on the, on this forecast benchmark, which is the closest thing there is to like a shared community benchmark for forecasting, we think that this is state of the art. And so this is just showing you the Breyer score. This is the mean squared error, where lower is better. This is the performance of our system. And I think most excitingly, so this difference is not statistically significant, but it's at least statistically indistinguishable from expert human forecasters.
How do you define someone to be a super forecaster?
That's a good question. I think, so there are people who have a track record of producing excellent forecasts, and they're sort of hired for that purpose. So a lot of these people will come from, for example, the Forecast Research Institute. And so you have to undergo some training and then have some track record of making high quality predictions. Okay, and so in the next 10 minutes or so, I just want to tell you a little bit about, both what it takes to build this kind of multi-agent system, what we learned from doing so, and then what I think some of the most interesting open research questions are. And so in the interest of time, there's a lot going on here, but I'm going to focus just on these two components, or maybe just the first component. We'll see how I do on time. So the first is search, so trying to retrieve relevant information to inform your forecast at inference time. And the second one is this reconciliation or ensembling step, so trying to reconcile many independent forecasts into a final probability. Okay, and so just to motivate, why do we need search? As you might know, the pre-training corpus for all of the frontier or frontier-ish LLMs is on the order of 9 to 18 months out of date. And this is because it costs, by some estimates, $100 million to complete a single pre-training run. So it's not something you can do every day. And this is actually helpful for us for this problem because what we can do is we can evaluate the models on realized outcomes that we know that are beyond their knowledge cutoff. But I think common sense would also then suggest that we need more timely information to inform our forecasts. So the models might need more timely news to inform their predictions. So I think that was sort of our prior going in. But I think empirically, if you look at the rest of the literature, that's actually not been the case. So what I'm showing you here is a screenshot from the Forecast Bench leaderboard. It's taken a few days ago. And it's just ranking all the different methods that people have tried by performance. And you actually have to go all the way down to the 54th method before you find any submission that used some kind of inference time retrieval. Right, so there are 53 methods that just take an LLM with some prompt and some other scaffolding, but no news beyond their knowledge cutoff. And they perform better than the best method that actually has some kind of inference time retrieval of news. And I think what you might notice too is that the 22nd best method and the 54th best method are identical, but for the fact that this one actually uses news. So in this case, search actually made the forecast worse. And I think this is a feature in actually all of the other literature on forecasting. At best, search seems to make no difference and often will hurt performance. Yeah.
The model itself can call to the side, right? How would you know that it's not calling it?
Yeah. So that is disabled to prevent it from sort of retrieving the answer to the event in question. So any tools that are provided by us, and then we sort of try and enforce the right kind of date cutoff.
Wait, sorry. So maybe I have a question about these benchmarks. So you say these are actually benchmarks forecasting things that already happened?
Yeah. So there are events that have already occurred, but beyond the knowledge cutoff for all these models, which
so
is...
what are the super forecasters there?
In what sense?
I mean, they also know what,
Oh, sorry. So their predictions are frozen in time as of typically like mid-2024 for Forecast Bench. And now we can evaluate the models later. Yeah, sorry, good question. Okay, so this is a timeline of the kind of major improvements we made to our system. We tried all kinds of very clever algorithmic tricks and fine-tuning and various other things. But really what we found is the thing that mattered the most was just improving search. So every time we made an improvement to search, we would get some large gains, like on the order of 10%. And so we wanted to understand why this was. And I don't really have time to show you all the numbers, but I'll give you kind of the stylized takeaways. So one of them is the sort of what I'm going to call non-agentic search, which was the standard in the literature before, is arguably worse than no search. So these models don't behave like rational Bayesians. And so if all you do is you allow the model to generate a fixed set of search keywords and you execute them and you give it whatever information is retrieved, you can often do worse than a baseline that excludes that search. But if you instead allow the models to sort of iteratively call tools, right? So what I'm going to call agentic search, or condition the future queries on the results of past queries, you can actually improve performance quite a bit. That was one thing kind of obvious in hindsight, given where the field is moving. I think the more interesting thing, or at least more subtle thing, was that it's common practice in this literature to collect these evaluation sets from public prediction markets. So places where people will bet on the outcome of a future event, like will the Democrats win the House in 2026? And what that means is that you can actually read off market consensus. You can see like what is the market pricing in for this event. There's a 70% probability, let's say. It's kind of common practice in the literature to provide that number to these models. And I think you could see that that was actually acting as something like a sufficient statistic for information that the models might have to retrieve themselves. And so hard coding this in the prompt was kind of standard practice. And I won't make you parse this whole table, but what it's saying is that you can explain about 42% of the difference between not using search and using the best search that we know how to implement by just providing the models with this market price. So if you can find these sufficient statistics, that's great. But there's also sort of an artifact of the way that these models are evaluated. Okay, and then the second thing I want to talk about briefly that just turned out to be interesting methodologically.
So your results are also with access to this market predictions?
Yeah, so ours are. So I mean, we have basically all the variants here.
And this is for the past event, so at that point, these are like, what kind of market predictions are if this is a event?
Yeah, it's the predictions as of the date the question was originally posed. So it's like there's some date on which you want to simulate making the forecast. That's when the super forecaster predictions are frozen, market consensus is frozen, and ideally any access to news is frozen.
And is your search, whatever you're searching over, frozen also?
Yes.
Before that?
Yes, although it turns out to be tricky to enforce this, so we have a lot of, we sort of spend a lot of time in the paper trying to justify that we actually did that correctly. But yeah, that's the intention. Okay, and so I want to briefly talk about ensembling. So I think it's sort of well-established, folklore in the community now that if you want better reasoning, you should figure out how to do some kind of test time scaling for generating more reasoning tokens. So for example, this is part of how Google claims to have gotten from silver medal on the IMO to the gold medal is very aggressive parallel computation or parallel reasoning traces, and then trying to reconcile them after the fact. So there's a very straightforward analog of this in forecasting, which is you just sample many forecasts and you take the mean. Right? And we find, like, for example, the mean of 10 GPT-4o forecasts, very weak model, is comparable to a single O3 forecast, which is the strongest model we evaluated. And so this is just showing that. The Breyer score decreasing is a function of the number of forecasts that you average. And you can see very sharp improvements as you go even from, let's say, 1 forecast to 5 forecasts. I think another thing that's sort of obvious in hindsight is just the consequence of Jensen's inequality, right? And the Breyer score is strongly convex. So the Breyer score for the mean forecast is going to outperform the mean of the individual Breyer scores. So that turns out to be a strong baseline, but I think there are actually good reasons to avoid taking the mean. And I think there's some nice theory around this, and then also some good empirics that one can do. But one thing you can try to convince yourself of is that if there's some true latent probability P, and what you observe are noisy samples that are perturbed symmetrically around that value, the mean is actually not an unbiased estimate of that unobserved probability. And the reason is because the probability scale is truncated. So you're actually observing samples from a truncated distribution. Similarly, if you model these individual forecasters as Bayesian forecasters who have access to incomplete information, you can prove that they're going to regularize their forecast towards 50%. And then I think if you know a little bit about how these models are post-trained, there are reasons to expect this might also be true, that they're going to hedge towards 50%. And so all of these point in the same direction, which is actually you can do better than the simple mean by trying to push your forecast towards the extremes, so towards 0 and 1. This turns out to help quite a bit. You can get on the order of 5 to 10% improvements. This was, I think, the difference between sort of not being state-of-the-art and being state-of-the-art on this benchmark. Partially because it's the last thing we did, but it turned out to matter. And you can see here what happens to your forecast. I know these colors are hard to see, but in red here, in lighter red, is the original forecast. In dark red is the extremized forecast. And so that turns out to help a lot. Okay, and so I think I'm out of time, but yeah, just briefly, some takeaways. So one is hopefully I've convinced you that these language models offer a qualitatively new way of forecasting. Their strengths are complementary to classical statistical learning. And I think this problem is interesting beyond, sort of settings where you just care about forecasting, in that it's a natural benchmark for more general AI capabilities. Methodologically, this looks a lot like an information retrieval problem. And it turns out that simple ensembling techniques go a long way. And then finally, I'll say, we are a hedge fund, so I can't share everything that we're doing. But I think we're working hard now on specializing the system to harder, more market-relevant domains. And I think that's where actually a lot of the very interesting methodological questions actually arise, which is how do you sort of fine-tune the models for this task? Okay, and so that's it. I'll just say this is on archive. I would like to thank all my co-authors, especially Bradley Stady, who co-led this project, and our chief scientist, Chaz Seacon. And then I'll do a little bit of obligatory recruiting just to get my flight reimbursed. So if this sounds interesting, please reach out to us or come find me in the break afterwards.
Thanks a lot. There are already some questions during the talk, so maybe you can catch Rohan for other questions later. Yeah, next we have Kostas Kollias from Google, who will tell us about algorithms for online navigation platforms.
All right. Hi, everyone, and thank you for the introduction. So I will talk here about recent work from our group in Google Research, which is called Geo-Algorithmic Intelligence. And specifically, I will talk about applications of combinatorial algorithms in online navigation platforms, which include Google Maps, Waze, Apple Maps, and so on. Of course, specifically, we work on Google Maps. So some recent projects that we have worked on, whereby worked on, I mean, we include publication and implementation in the actual system, include routing of electric vehicles through charging stops on long trips, an algorithm that computes a large number of diverse alternative routes in road networks through utilizing electrical flows and their decompositions. An explainable routing system, by which I mean in cases where the route that we provide to the user, it's much different than the one typically presented at that time of day. We have a linear programming-based solution that identifies a small set of edges that are closed or more congested than usual that we can present as explanations. And finally, a system for monitoring queue lengths in the road network, meaning like the lengths of traffic jams and their delays and so on. And now moving forward, I will talk in a little more detail about the first one and the last one, so about routing electric vehicles and about monitoring queue lengths in road networks. Okay, so I will start with a somewhat simplified model of electric vehicle routing. So think of the case where we're given a directed graph that has on each edge a cost. So for now, one of the simplifications is that you can treat this cost as the length, the travel time, and the equivalent of the energy spent. So Let's assume for now that all these things are proportional and have one edge cost. Then we have the set of nodes. Some of them have been painted blue, which means they are labeled as charging stops. Each one of them also has some cost that represents the time spent charging at that stop. And a second simplification that we will make here is that if we make a stop, we will charge up to the full battery capacity of the car. All right, then each query comes with an origin node S, a destination node T, and finally we're given the range of the car, which is how far it can travel without needing to recharge. All right, then the output that is required is a path of minimum cost that starts at S, finishes at T, and does not have any subpath of length R that does not visit a charging stop. So it does not run out of battery. All right. So I think this is a nice homework problem for Intro to Algorithms class. Let's see how we would solve it. Now, imagine any point where we're standing either at the start or at one of the blue nodes, one of the charging stations. Well, I mean, traveling distance R away from it, we will have to do one of two things, either reach the destination or get to another charging stop. All right, so essentially, here, after making a quick check to see if T is reachable from S within distance R in the beginning, then the problem becomes essentially hopping between charging stops until you reach the destination. All right, so what we're going to do is we're going to build an auxiliary graph that will have direct edges from S to all the blue nodes and to T, if possible, that are reachable from S within distance R. All right, so the cost of that edge will be equal to the cost of the shortest path between the two endpoints that we're connecting. We will do the same thing to the destination, adding an edge from all blue nodes that can reach it within distance R, and then we will take care of all the hops between blue nodes. All right, so we will connect blue node A to blue node B if the shortest path between them is within distance R. So observe that the most of these edges are in the last set, and this can be pre-computed offline. So when a request comes, you can simply connect S and T to this auxiliary graph, run the shortest path computation on this graph, and you will get the optimal way to go from S to T, hopping through some charging stops in between. Right? So now let's remove the two simplifications that we made. Assume that on an edge that we travel, like going from station A to station B, the energy cost can be different than the cost of the travel time cost, right? And then the second thing that we can do is we can have partial charging at charging stops. The reason could be is that maybe we're standing on a charging stop that is slower than one that comes later, so I want to charge just a little bit here. Or that, as you know, charging speed, as you might know, charging speed is not uniform. So it's faster to charge from 30 to 40% than to go from 80% to 90%. So the way to handle these generalizations conceptually, so this is not exactly what happens at the implementation level, but the conceptual solution is that we can discretize the battery level. So I should say first that if we don't do this rounding, this discretization, if we try to solve it completely, it's not possible. The problem becomes NP hard the moment we have two different edge costs. But if we allow ourselves this kind of rounding where we discretize the battery level and assume that the battery can be 1, 2, 3, up to 100, let's say, then I can have corresponding copies of the graph for the different battery levels. So one copy for 100%, one for 99%, and so on. As we travel from one node to another, we'll be going down these layers. So if I'm going to spend 20% of my battery, I start at some layer X and I end at layer X minus 20. But when I reach a charging stop, I go up. And so I will be suffering the travel time cost as I go down. I will be suffering the charging cost as I go up. Right? And then solving on this graph again will give you the correct solution for this generalized version. Some follow-up questions, like one problem that came up from the practical side of things is that in certain regions, building this auxiliary graph, like for example in Belgium or Germany, where charging stops are very dense, ends up with a very large number of edges, like edges in the billions, for instance. And on the product team that we were collaborating with wanted to have very detailed information on each one of these edges to be able to compute the battery spent for each vehicle that would come in as input. So the graph ended up being very large and could not fit, for instance, in the memory of the server. Right? So there, to handle this problem, we applied spanner construction algorithms, specifically simple generalizations of the greedy geometric spanner. And there we were able to keep 1% of the graph with a 1% error in the induced costs. A second extension would be an online formulation of the problem that we did for our publication. So think of the case where the charging stops are busy, right? So there are other users that are charging there. And we don't have a good understanding of the waiting time that we would suffer at that charging stop as we drive there. So I think there's a very long highway that we're driving on. It has some candidate stops on it. And I don't know of this hidden cost until I get near that station. But as I drive, without knowing far into the future what is happening, I need to make a decision. Am I going to stop here, or am I going to keep moving towards the next stop? And like informally here, the main result that we had in this setting is that if the look ahead, like how far into the future do I have a good understanding of the waiting costs, is less than the range of the car, then theoretically there's nothing that you can do. The online ratio is infinitely high. Whereas the moment the look ahead reaches the range, then you can achieve a constant factor ratio. All right, and with this, I will move on to the second topic, the monitoring of queue lengths. So these platforms that I mentioned route large numbers of requests every day. And to do so, it would be best to have accurate estimations of the delays on road segments, or equivalently the lengths of the queues at traffic jams. So this information is typically provided in a live manner from the devices that are in the network, like user phones, for instance. Okay? And what these devices can tell us is, as they're driving on a segment and they know their GPS position, they know how much of that segment is ahead of them, and they can infer, in some sense, the number of cars that are ahead of them in the queue, but they don't have any information about what happens behind. So if these cars or packets, if we can call them, in the queue, can tell us at any point their position, their offset in the queue. Right? So what we want here is for these packets to give us information infrequently, because doing so frequently imposes load both on the server from processing all this data and on the device itself by draining battery. But we also want, of course, to maintain accurate estimates of the length queues, of the queue lengths. So the model that we use here focuses on one road segment at a time. It models the road segment as a first-in, first-out queue with events that include arrivals and departures. And as I said, at any time, a packet in the queue can emit its position. The packets want to ping in frequently, and the server wants a small average reconstruction error. Now, some definitions to state the problem itself. We will write opt for the average queue length, essentially, over the time that we're monitoring. So 1 over t, capital T, which is the number of time steps, of the sum of the departure time minus the arrival time of each packet, which is equivalent to 1 over capital T, the sum of the queue lengths. Right? So if we define this as opt, and then for each time we make a prediction E of t, we will write alg for the average expected error over the course of the time that we're monitoring the queue. Right? And what we're asked here to do is provide an algorithm that minimizes the total number of pings that are sent to the server, subject to achieving an error that is less than or equal to epsilon times the average queue length for some parameter epsilon. So I will talk about this one class of policies that handles the case where the departure rate is fixed. So we know that at every unit of time, one car is leaving the road segment. Arrivals can be arbitrary. All right? So this class of policies is called ping on arrival, which means that the packets themselves only consider sending us information the moment they enter the queue. So if we have a fixed departure rate, you can see that this is sufficient. So a new car comes. If every car tells me on arrival what happens, I have an exact understanding of the queue length. Right? So some car comes, it tells me I am the 10th car. So I can start, I know that the queue at this time has length 10. Every time step I decrease it by 1 until a new car arrives and tells me the new length and so on. So in that setting, what we're trying to do here is assign some probability of pinging. We don't want every car that arrives to tell us the length of the queue. The intuition is that we want queues that are relatively empty to have high probability of pinging. So if there's 1, 2, or 3 cars and so on, we want the cars to tell us that the queue increased in length by 50%, right? But just one arrival. If there's 1,000 cars there, I don't want to have to, like 1,000 times here, the queue is very long, the queue is very long, and so on. Hear it over and over again. I want, as the queue length increases, the probability of pinging to decrease. And specifically, if we use the function that is in the statement of the theorem, we achieve this small reconstruction error. And in follow-up results, one of the follow-up results that are included in the paper is that that policy that I showed before is essentially asymptotically optimal. So it's this number, this amount of pings is necessary for achieving a small reconstruction error. And the paper also includes another class of policies that ping more than just at arrival time. And they are designed to handle the case where the departures are not constant rate, but they're stochastic. And we saw that this class of policies also has a small number of pings in the sense that it's only logarithmically more than the ones that ping on arrival policies do, which are the ping on arrival policies are optimal for a simple setting. Ping continuously policies handle a more complex setting and yet don't do many more pings than the ping on arrival counterparts. And with this, I have concluded everything that I wanted to say, and I'll be happy to take any questions or discuss later.
Okay, maybe a quick question as the next speaker sets up. All right. Thanks again. Great talk. Yeah, next we have Giuliano Losa from Stellar Foundation on Federated Byzantine Agreement overview and some open questions.
Right, hello everyone. So my name is Giuliano. I'm from the Stellar Development Foundation. And so today I'll give not so much of an overview, but an introduction, I guess, to this Federated Byzantine Agreement model, which is a model for distributed systems that's at the basis of the Stellar network, which is a blockchain network that's developed by the Stellar Development Foundation. So the Federated Byzantine Agreement model, so it's a somewhat recent addition to a long line of work that started in the 80s and maybe earlier, where people were building systems that tolerates both failures and asynchronous communication. And they did so in models that were increasingly adversarial and increasingly open. Up to the point of today's so-called permissionless blockchains. There are systems that allow anybody to come in and participate and access the system. And we care about that at Stellar because the mission of the foundation is to provide global and equitable access to financial systems, and those permissionless blockchains are great at that. So one common thread between all those works here is that they're all based on what we call quorum systems. So let's see what a quorum system is in very simple terms. So abstractly, it's just a set of sets that is going to describe failure assumptions about parties in a network. So to take a very simple example, let's say we have 3 servers in our network, A, B, and C. we define the quorum system as our set here of so-called quorums, AB, BC, and CA. So any two out of three of our three servers. And this encodes the assumption that at least two servers will remain available throughout the life of our system, or equivalently that at most one will fail. So very simple. But stating our failure assumptions in this very simple structured way, so it allows us to design distributed algorithms in a principled way, including blockchain algorithms. So let's continue our very simple example. Let's say we have a client here that wants to store a file on our three servers. So it sends the file to the three servers. But because we have an asynchronous network, the message going to A is very slow. But the client knows the quorum system that we're using. It's part of the configuration of the system. And this quorum system is telling us that the client cannot wait for more than two responses or to store the file at two servers, because three servers is not a quorum. One server may fail. And from the point of view of the client, the server A might as well have failed. So it stores the file on two servers. And then later, maybe we have another client Y that wants to retrieve the file. And for a similar reason, it cannot wait to hear from the three servers. It has to move on as long as it hears from two servers. But here, things will work out. It will get the file because we have the properties that every two quorums intersect. So even though our two clients, they use two different quorums, the quorum intersects and the file is transmitted. Great, so in general, a quorum system doesn't have to be like a simple majority like we just saw. It can be any set of sets with pairwise intersection if we're considering crash failures. And so some more general examples include parties that we assign weights to, maybe representing how reliable they are, and then we use the weights to define the quorums. Or hierarchical quorum systems. Let's say here we have 3 data centers, and we're going to assume, okay, at least 2 of our data centers are going to remain online, and inside those data centers, at least 3 servers out of our 5 servers are going to remain online, and that's our quorum system. Now, if we require stronger intersection properties, namely that every 3 sets, not 2, but 3 intersect, then we can even tolerate so-called Byzantine failures. There are failures where our servers can not only crash, but they can also come under control of an adversary that will not follow our protocol. So this is great, but all those quorum systems, they seem to require some kind of gatekeeper to tell us, okay, so which are the servers and what is the definition of the quorum system. And that's not great for our goal of building open access systems. But luckily, Bitcoin showed us that actually we can build the systems we want in a totally open way. But Bitcoin did so with a new mechanism called proof of work. It's completely different from quorums. And the thing is that it's kind of expensive and slow. So the natural question is, can we take this idea of quorum systems that are much more efficient and cheap and use them in permissionless networks? So of course, the answer is yes, and a very popular way to do this is so-called proof of stake. That's famously used by Ethereum. But we're not going to talk about that. Instead, we're going to focus on this alternative answer called Federated Byzantine agreement that's used by Stellar. So if you think about the quorum systems we just saw, you ask yourself, well, how can we make this work if we don't know who is in the system? So one way to do it would be to just say to the parties that want to join the system, well, you can join the system whenever you want, and you just choose for yourself a quorum system. And maybe different parties will choose different quorum systems. And actually, that can be fine. This is analyzed in a very recent paper, actually, by Alpos et al. 2024. But the problem is that it works fine as long as our parties choose quorums that overlap enough. And if we have a totally open systems where some parties are complete strangers, this is going to be hard to obtain. So in Federated Byzantine agreement, we start from a similar idea where we're going to let all the parties make their own subjective assumptions about failures in the system, but not only about failures, also about other parties' assumptions. So very concretely, so we allow any party who wants to join the system to join, and a party P, when it joins, has to pick a family of sets that this time we don't call quorums, but we call quorum slices. So there are different things. And those encode assumptions about failures, namely that our party P is going to assume that it has at least one quorum slice S, such that first, all the members of S are going to be available and well behaved, so that's like before. But second, for each member of S, the assumption of that member are also going to be satisfied. And so this creates a kind of recursion. So let's see this in a concrete example. Here we have parties 1 through 9 in our system, and we're going to focus on party 1. And so let's say that party 1 defines quorum slices that consist of any 2 out of the parties 2, 3, 4. So in order to satisfy one's assumptions, we would need to have, let's say, those 2 parties, 2 and 4, that will be available and well behaved throughout the execution. But according to item 2, we also need the assumptions of those parties to be satisfied. So maybe those are the assumptions of those parties, and we could satisfy them by assuming 6, 7, and 8 are going to be available and well behaved in the execution of the system. And again, applying item 2, the assumptions of those parties must be satisfied. So let's say they define their quorum slices as 4 out of those 5 in the middle here. So we can satisfy this if this additional party is available and well behaved. And now we've reached some kind of closure where the assumptions of all the parties we've selected are satisfied. And this is what we call this time, for real, a quorum in the Federated Byzantine agreement model. So there may be other parties in the system, like party 11 here, that has quorum slices that are completely disjoint from party 1. But if we try to build the quorums of that party, we'll realize that they're going to have a similar shape, and they will all intersect with the quorums of party 1 in the middle. And so we obtain quorum intersection transitively in that way, and that's the main idea behind Federated Byzantine agreement. So this is used and has been used live in the Stellar network for almost 10 years. And here you can see a kind of map or a representation, although it's not very clear. We don't see the edges, I guess, of the quorum slices of all the parties participating in the Stellar network, as it was a few months ago. And if we were to draw the quorums, we'd see something like this, where all the quorums intersect in the middle. And of course, this intersection of quorums is not guaranteed. There's certainly configurations where quorums do not intersect, but we believe that in practice this is not likely to happen, and we call this the internet hypothesis. So this hypothesis starts with the observation that the internet is a similar kind of network, and it remains robustly connected, even though there's no central authority that manages the peering relationship between autonomous systems on the internet. And so the hypothesis is that this will be true also of a global deployment of Federated Byzantine agreement, because the similar forces will be at play in practice. All right. So compared to previous simpler quorum systems, there are many interesting phenomena and challenges that arise in Federated Byzantine agreement. I'm not going to go through all this list, but I'm just going to point out that so in 2019 we published 2 peer-reviewed papers about this. One at SOSP about the more system aspects of the work, and one at DISC about the distributed computing theory behind this. So if you're interested, I encourage you to have a look. But those papers, they didn't resolve everything. And with the few minutes that I have left, I just want to go over a few challenges that remain that I think are interesting research questions. So the first one is that we don't know if we can match the latency of algorithms that are designed for classic quorum systems. So here you see the optimal kind of message pattern achievable in a classic quorum system by this algorithm called PBFT. And we know we can achieve something similar, but at a cost, worst case message complexity cost that is cubic, whereas PBFT is quadratic. So that's the first question, pure distributed algorithms question. Second question, so these consensus algorithms that are used to maintain blockchains, they often rely on leaders to perform efficiently. And in a classic model where you have the list of all participants, you can just rotate the leader role round robin, let's say. But here, we don't know really how to elect a good leader in our system. So we have this big graph of quorum slices, which is actually a hypergraph. And so some graph theory here will probably help, and that may be an interesting problem if you're interested in graph theory. And in general, there are many questions that we want to ask about the structure of this hypergraph that we obtain. Some of them we know are NP hard. Some of them we also don't know how to solve at all, or their complexity class. So there are some interesting questions there. Third question. So there is a building block that's being heavily used now in new blockchain algorithms, where we use erasure codes to efficiently disseminate data in the system. So the idea is that we have a big chunk of data that we want to store in the system. So we create a code word out of it that we can separate into individual chunks. And then we assign one chunk to each party in the system. And for some distributed algorithmic reasons, we want to be able to recover our original data by just asking a quorum for their chunks. And so this is easy to do with like standard Reed-Solomon codes if we have just k out of n quorums. But we're not sure how to, I mean, we have some ideas, but we're not sure how to generalize this to just any set of sets or the Federated Byzantine Agreement quorums. And finally, I will conclude with this one. There's another tool which is really useful in a standard blockchain consensus algorithm. It's threshold signatures, so which allow us to prove with a constant size compact signature that k out of n parties signed some data. And here, the question is a little bit similar to the one with erasure code. It's how do we generalize this to arbitrary sets of sets, not just k out of n, and also whether we can do this without requiring any expensive setup or maybe no setup at all, because in our model, the quorums, they're liable to change at any time because the participants can change their configuration whenever they want. Okay, so that concludes my talk. I just want to point out that if you're doing research related to blockchain in general, or you're interested in those questions that I just asked, we have an academic research grant program, so which is where you can submit proposals every quarter. And also we have a research group at Stellar, of which I'm a member of, and we want to expand our research group and grow it. And for this, we are looking for a director of research. So if you're interested, or if you know someone who might be interested, please direct them to the job posting. And that's it.